Dear students, I welcome you all in this class on analog and digital communication subject. Today we will start a new topic, that is pulse code modulation. In the previous classes, we had completed the concept of pulse modulation, where we discussed pulse amplitude modulation, pulse width modulation, and pulse position modulation. Today we are going to discuss pulse code modulation, and this pulse code modulation is the first step towards your concept of digital communication. I hope you will enjoy the topic of pulse code modulation. So, dear students, obviously for any modulation technique, our starting point is our information signal or the message signal, because our prime objective is to transmit information signal or message signal from one place to another place. And we know that in case of pulse related modulation techniques, our message signal is transmitted with the help of pulses. We have seen that thing in PAM, PWM, and PPM. Now in pulse code modulation, what happens, our message signal is also transmitted with the help of pulses, but those sequence of pulses, it is coded pulses. Okay, means the pulses will be coded with some code. These things will be clear as we move forward. Okay, another important point in pulse code modulation is that the signal is represented in the discrete form. Okay, and the discreteness is present in both time and amplitude. I hope you are able to appreciate this point. What I want to say is, in PAM, in PWM, and in PPM, whatever signal we observed, that was discrete in time. Means there was discontinuity, or that there was discreteness in the time domain. Okay, there was gap in the time, there was discontinuity in the time. Whereas in case of pulse code modulation, we have discreteness present in time as well as in the amplitude. Okay, what does it mean? Discreteness means some finiteness, or some finite number of levels, or some finite number of samples. So in case of PCM, we have our signal represented in discrete form in both time and in the amplitude. This is very, very important point that you should understand and you should take care of. And this thing will be further clarified in the coming slides. Okay, and in case of a PCM transmitter, the basic operations which are involved, these are your sampling, quantization, and encoding. In case of PCM receiver, obviously the reverse of operations which takes place in the transmitter takes place. So the basic operation in PCM receiver include the regeneration of the impaired signal. Why are we saying impaired signal? Because once our signal transmits from transmitter to receiver, there will be some distortion in the signal due to noise in the channel and noise in the system. So we need to regenerate our signal at receiver side. Then in PCM receiver, we need to decode. Since we have encoded at the transmitter side, in the receiver side, we need to decode our signal. And then finally, we need to reconstruct our signal samples back. Okay, so as I told you, in transmitter, we have an important operation, sampling, in case of PCM. So we need to reconstruct our sampled signal back to the original signal. Okay, so these are the main features of pulse code modulation, which will be further clarified in just few minutes. Okay, and why are we studying pulse code modulation? Because in PCM, the effect of noise is significantly reduced. As I told you that this is the first step towards digital communication system. So we know that the most important advantage of digital communication system is that the effect of noise is significantly reduced as compared to your analog communication system. And this thing will be clear to you also as we progress further in this topic on pulse code modulation. I hope this thing is clear. So students, these are the basic elements of PCM transmitter. So in case of PCM transmitter, I just told you in the previous slide, we have three basic operation. One is sampling, another is quantization, and the third one is encoding. We will discuss all these operations one by one in detail. And once you understand what is sampling and why sampling is required, then what is quantization, why quantization is required, and similarly the encoding part. If you are able to understand these operations, then you can appreciate the concept of pulse code modulation effectively. Okay. And this thing I have already told you that PCM represents our signal in discrete form in both time and amplitude. Okay. So this thing has been shown here in the form of block diagram. In PCM encoder, we have sampling, we have quantization, and we have encoding. So we will take up one by one each of these operations in the coming slides. So you can see here our starting point is the analog signal, which is our modulating signal. Okay. In pulse modulation, we have already seen that we will be sampling our signal, which will give us discreteness in the time domain. And we saw sampling in the PAM also. So same kind of thing here. So sampling gives us discreteness in time. Okay. And then I told you that we need discreteness in amplitude also. So this quantization operation will provide us discreteness or finiteness in the amplitude domain. Okay. So sampling gives us discreteness in time. Quantization gives us discreteness in amplitude. And encoder, we already know that we encode our signal in the form of ones and zeros. So this is the main crux of your pulse code modulation system. And these can be considered as the main elements of your PCM transmitter. So now let us talk about sampling first in detail. So as I told you that we are moving from analog communication to digital communication. So sampling process is the first step to convert your analog signal into digital signal. Okay, so that way also sampling is very, very important process or very, very important part of the steps that are required to convert an analog signal into digital signal. Okay, before we move to sampling, we need to discuss that why at all we need to convert our analog signal into digital signal. One reason I told you in the previous slide, that in case of PCM system, the effect of noise is significantly reduced. So obviously the noise will be very, very less in case of digital signal as compared to analog signal. Obviously, when noise will be lesser, then the quality of the signal will be better. So that way, our ultimate objective in any communication system, be it analog or digital, our objective is to receive the replica of the information signal at the receiver side. So whatever information signal, original information signal we have transmitted from the transmitter, we need to have the exact replica of that information signal at the receiver side. And obviously, the quality of that information signal received, it should have sufficient quality with minimum noise. This is our ultimate objective. Okay, apart from that, we need to notice one more thing. We are saying that the quality of the signal received, it should be sufficiently high quality signal. Okay, so I'm not saying here that the quality of the signal should be absolutely 100% good quality. See, our human eyes and human ears, these are the natural receivers which God has provided us. Okay, and our eyes and our ears cannot distinguish the quality of the signal beyond certain quality level. Okay, say if out of 10, I say that the quality level that I achieve is 9 out of 10. Okay, and if I say that quality level is 9.5 out of 10, then our eyes and our ears may not be able to appreciate whether there is some change in the quality that we are perceiving. So our eyes and ears, that is your natural receiver, they have limitation that beyond certain level of the quality, we are not actually able to distinguish whether the quality has improved or not. So if we cannot distinguish the quality, what is the need of investing our energy into the improvement of the quality? So that's why we always try to have sufficient quality, not the absolutely best quality. Okay, so the quality that we can notice, that we can appreciate, we only work up to that level, because we do not need to invest unreasonably in order to improve quality beyond a certain level. So that way, if I talk about analog signal, we know that our analog signal is represented like this. And in analog signal, we know that there are infinite number of values or infinite number of voltage levels present in the time domain as well as in the amplitude domain. So if you look at analog signal carefully, I have infinite number of voltages present at infinite instances of time. Both in both domain, I have infiniteness present. So obviously, if I have infinite number of voltage values, so if I can, maintain quality in all the infinite signal values, so obviously I'll be getting the best quality. But there is no point in ensuring that quality in all the infinite voltage levels. Okay, so what we do, instead of maintaining or instead of having infinite number of values, we can think of having finite number of values in the time domain as well as in the amplitude domain. So out of those infinite values, we will select certain finite number of values, certain fixed number of values. Okay, and those values will then be handled by our system or will be processed by our system. Okay, and if we try to improve the quality of only those finite signal values, okay, at finite instances of time, if we want to if we improve their quality, if we reduce noise at that level, then we can say that we have been able to achieve sufficient amount of quality. Okay, so there is no point in investing unnecessary effort on the quality which cannot be appreciated. So that's why instead of dealing with infinite number of values in analog signal, we deal with finite number of values in digital signal. And so obviously where we have limited number of values, we can think of improving the qualities of those values. Okay, and sampling is first step in introducing finiteness, or you can say the discreteness in the time domain. Okay, so what we will do in sampling, that we will sample the values at different instances of time, instead of infinite instances of time. Okay, so this is what sampling gives us. I hope all of you have been able to understand this main concept of the sampling process. Next. So, as I told you, our original or the natural signal is having infinite number of values, both in time as well as in amplitude. And once we do the sampling in time, then obviously, since we are considering finite number of values, so some deliberate distortion has come into the original signal. Our original signal was analog signal. Okay, and in that original analog signal, we have extracted certain samples, okay, in time, okay, with the help of which we can represent or we can approximate our or approximately represent our original information signal. So that way I will say that due to sampling, some deliberate distortion into the original information signal, which was analog one, that has been introduced. And this deliberately introduced distortion is due to the finite number of samples in time. Okay, now since we have considered finite number of samples in time, okay, what we want? We want that from these finite number of samples, we should be able to reconstruct our information signal in an approximate manner, and it must be able to provide us reasonably good quality. See, what I want to say that I had one analog signal with me, okay, it had infinite samples. So instead of infinite samples, I chose certain samples values, okay, say these 6 values. So by looking at these 6 values, I can easily make out that, okay, approximately my signal may be like this. Fine. So the number of samples that I take in order to introduce discreteness in time, I'll have to make sure that those number of samples that I have taken, they should be able to give me a fairly good idea about the original shape of the signal. Okay, say if I take only 2 samples out of this, say one sample here and one sample here, so then there may be infinite number of possibilities about the shape in this signal. It may be like this, it may be like this, it may be some other shape. Or if I would have taken, say, only one sample, then from this one sample, I cannot make out anything that could help me in identifying whether my original signal is equivalent to this sinusoidal or not. So that's why, even though I am considering finite number of samples, I will have to take care that the number of samples should be sufficient enough so that I can reconstruct that signal at the receiver side with reasonably good quality. Okay, so sampling never says that you take minimum number of samples. Yes, obviously we will take minimum number of samples with the condition that those minimum number of samples must be able to help us in reconstructing our original signal back. Okay, so these requirements from the samples, they are formalized in the form of sampling theorem. Okay, and we call it sampling theorem. This is a formal statement. All of you must remember this sampling theorem, and this is very, very important. And I am stating here sampling theorem for low pass signal. I'll just tell you what is the meaning of low pass signal. First, let us look at the statement of sampling theorem. So I'll first explain the statement number 2. Though 1 and the 2 statement, both statements are nothing but equivalent of each other. Let us see statement number 2 of the sampling theorem. According to this sampling theorem, a band limited signal of finite energy means my original signal is band limited. This is one important word that you should note here. A band limited signal of finite energy which has frequency components less than W hertz. What does it mean? That the maximum frequency which is present in this band limited signal is W hertz. In that case, such signal can be completely recovered. As I just told you, can be completely reconstructed. So such signal can be completely recovered from knowledge of its samples. Means we can reconstruct our original signal from its sampled signal, okay, if we take those samples at the rate of 2W samples per second. Okay, what does it mean? 2W samples per second means if the maximum frequency which is present in the signal that we are sampling is, say, FM, and we want to reproduce this signal or reconstruct this signal from its sampled signal, then we need at least twice of FM samples per second. Okay, means twice the frequency, twice the highest frequency of that signal. We need minimum. This is the minimum condition. twice of FM is the minimum condition. Practically, it must be greater than or equal to twice of FM. In no case, it should be less than twice of FM. I hope you are able to understand this sampling theorem statement. Okay, and this sampling rate, this minimum sampling rate, which is twice of FM or 2W, one and the same thing, it is called Nyquist rate. And reverse of Nyquist rate is called Nyquist interval. We know that reverse of frequency is time period. So 1/2W is nothing but the Nyquist interval. Fine. Now the statement number 1. The statement number 1 is nothing but the same as that of statement number 2, but both are equivalent. Statement number 2 was in frequency domain, whereas statement number 1 has been explained with respect to time domain. Okay, so you can see here again a band limited signal of finite energy which has one frequency component less than W hertz, it is same, can be completely described, okay, can be reconstructed or can be fully explained by specifying the values of the signal at instances of time. So here we are considering time separated by 1/2W second, means the time period of the samples that we are considering in that signal, they must be separated by 1/2W second, means the reverse of 2W samples per second. Okay, so this is how we state sampling theorem. I hope all of you have been able to understand the statement of sampling theorem. Okay, and I asked you to note this word band limited. Band limited means that my signal has finite bandwidth. If I represent the spectrum of the signal like this, in frequency domain, the maximum frequency is say FM, okay, and my x-axis say frequency, that is F. So band limited means my signal is having finite bandwidth. I cannot sample infinite bandwidth signal. My signal must be having finite bandwidth or band limited. So if you want to sample infinite bandwidth signal, you will have to pass it through a filter, okay, band pass filter, so that your signal becomes band limited. Fine. And then another point I asked you to note, that is low pass signal. Low pass signal means your signal frequencies are from 0 to some frequency, say FM. This is low pass signal, means whose pass band lies in the lower range of the frequency. We also have sampling theorem for the band pass signal. So for band pass signal, your signal will be having certain band of frequencies. Okay, so from say from F1 to F2. So that is for band pass signal. So sampling theorem for band pass signal I am not discussing here. That may add complexity to the things. But if you understand sampling theorem for low pass signal in a complete manner, then it will not be a difficult job for you to understand sampling theorem for band pass signal. Okay, so I hope all of you have been able to understand the concept of sampling theorem or the statement of sampling theorem for low pass signal. So students, after looking into the statement of sampling theorem, now let us talk about its proof. We will explain sampling theorem mathematically. So if you remember, I have already proved sampling theorem during pulse amplitude modulation. Though I did not explicitly said at that time that this was the proof of sampling theorem. But if you look at this slide, you must have noticed that same thing we have already studied in pulse amplitude modulation. If you remember, we also talked about natural sampling and flat top sampling in case of pulse amplitude modulation. So in case of pulse amplitude modulation, we had introduced finiteness or discreteness in time domain, and there also we talked about sampling. Okay, so mathematically, if I say that, or mathematically, if we want to prove sampling theorem, how can I prove sampling theorem first? So if we look at this slide again, so proving sampling theorem means that if I consider a sampled signal, Okay. And I can show that my signal can be completely recovered. Okay. If my sampled signal is taken at the rate of 2W samples per second, and I can recover my original signal back. So I can say that my sampling theorem is proved. So same thing I'm going to do here. So if you remember, this is our ideal sampling signal. Ideal sampling signal will have impulses, okay, where I'll be taking samples exactly at that instance. But practically, we cannot have impulses for sampling. We have pulses for sampling. Okay, so we take train of pulses to sample our modulating signal. So our modulating signal has been represented by Ft. My sampling pulse train is represented by Fct, having amplitude A, duration tau, and time period Ts. So here the mathematical analysis is being carried out for the case of pulses having duration tau. And if you make this duration tend to 0, if the duration of the pulse becomes 0, then it becomes impulse. Okay, so this analysis or the proof of sampling theorem, if you make your time duration tau tend to 0, okay, then your tau can be replaced with d tau. Okay, all of you know differentiation or infinitely small component is d tau. So if you replace that, then that analysis applies to your impulses. Okay, so for the sake of simplicity and for the sake of your understanding or practical concept, we are taking here pulse train instead of impulse train. Okay, so this is my original modulating signal. This is my train of pulses that helps me in sampling at a particular instance. And if I want sampled signal, then mathematically I need to multiply my modulating signal and I need to multiply my sampling pulse train. If I multiply these two, okay, then mathematically I'll be able to get my sampled signal. This is my sampled signal. So if I multiply these two, I get this. So mathematically, I'll represent my modulating signal. I'll be representing my train of pulses. I'll multiply them and then I'll see the spectrum of that. And if I'm able to recover my original signal back out of that sampled signal spectrum, then I can say that my sampling theorem is proved. Okay, so if you remember, I represented my periodic train of pulses with the help of Fourier series, and this is my Fourier series representation for periodic train of pulses, where Cn is your Fourier series coefficient, and this is the representation straightforward in the form of summation of cosines. Okay, and this we have already covered during our discussion on pulse amplitude modulation. Next. So here again we have taken the amplitude of our sampling pulse train as 1 and the time period has been taken as Ts. If you substitute these values, my sampling pulse train becomes like this. Okay, this is again the coefficient of Fourier series. Fine. And as I told you, my sampled signal, which is shown on the right hand side of my slide, will be obtained by multiplying these two signals. So if I pass these two signals through a multiplier, mathematically F and FCT are multiplied, I get sampled signal. So you can see here that I am multiplying and this is what I get as sampled signal. Means this. Okay. So as I told you in sampling theorem, for sampling theorem to be executed or to be implemented, we need at least 1/2 FM time period between the samples. Okay, according to sampling theorem, or we need twice of FM samples per second, where FM is the maximum frequency. So if we ensure this thing, then we should be able to recover our original signal back. Let us see whether that happens or not. This is what happens. So this is our sampled signal. Okay. Then this is spectrum of my original signal, means spectrum of this signal. frequency spectrum means I am representing this signal now in the frequency domain here. This is the same signal, but in the frequency domain. Fine. And this is my sampled signal. I have represented this sampled signal in frequency domain here. So this is my original signal in frequency. This is my sampled signal in frequency. Okay. And if I had explained in pulse amplitude modulation that how do we get this sampled signal frequency domain representation from this. Okay. By observing that the two frequencies will be added when multiplied, they will be added and we get such kind of thing. So you can see here that this is exactly same as my original signal. Okay. This portion is corresponding to this part where my FT modulating signal is multiplied with cosine of twice FM, means your twice FM is the central frequency and your modulating signal is centered around that. Then I have the modulating signal centered around 4 FM, then to 6 FM like this. Fine. So if you look at this sampled signal frequency spectrum carefully, you can see that my original spectrum is present at 0 to FM. So if I pass this thing through low pass filter, my original signal can be recovered. And how this thing has become possible? This thing has become possible by ensuring that my sampling time period is 1/2 FM. If I do not ensure this, I will not get such kind of thing. Okay. So this is how I can prove my sampling theorem, that I can recover my original signal back from this sampled signal. So if you again see carefully, so this is FM, this is twice of FM. Okay. So means your sampling frequency is twice of FM. The gap is exactly FM. FM here, twice of FM. Fine. So this is the proof of sampling theorem. Now we also need to look into what happens or how does this frequency spectrum look like if my sampling frequency either becomes greater than twice of FM or it becomes less than twice of FM. So let us see that thing in next slide. So the first case, when my sampling frequency is less than Nyquist frequency, and we call that case as undersampling. Okay, in case of undersampling, see what is happening in case of exact sampling. In case of exact sampling at Nyquist rate, your signal components, they are exactly adjacent to each other. Neither there is gap nor there is any overlapping. Okay, but if my sampling frequency, this is my sampling frequency. So if my sampling frequency becomes less than twice of FM, means my sampling frequency will shift towards left side. It means there will be overlapping here. So that is what I am trying to explain, that if my sampling frequency becomes less than twice FM, I call it as undersampling. Okay, and my spectrum becomes overlapping. So if this was my original spectrum of the signal, then this is what has been done. Overlapping is taking place instead of just adjacent. Had it been exactly same, then your spectrum should have looked like this. Okay, but now it is overlapping due to undersampling. Okay, this is overlapping. This is overlapping. And this overlapping of the frequency spectrum, that is called aliasing. This phenomena is called aliasing. Fine. And obviously, if aliasing takes place, then we are not able to recover our signal back because my sampling frequency is less than Nyquist frequency. Then next case is oversampling. Oversampling means my sampling frequency is greater than Nyquist frequency. In that case, my sampling frequency will shift towards right hand side. Means there will be some gap here. So in that case, if this is my spectrum of original signal and this is my sampling frequency, it is greater than twice of FM, means it has shifted towards right side. So because of that, some gap has come here in between the adjacent spectra. Okay. So in case of oversampling, we get band gap. So these are the two things that happen when I deviate from exactly Nyquist frequency. So the question is, practically what happens? Practically, we oversample the signal. Okay, we take our sampling frequency more than the Nyquist frequency. And why do we do that? Because if we keep our sampling frequency more than our Nyquist frequency, then we will have a band gap. And I told you that how do we recover our original signal back? We recover our original signal back by passing our original signal through a low pass filter. So this thing will be passed through a filter. And we know that how does your response of the filter look like? So if this is my spectrum, so my filter response, it should be like brick wall. The actual filter response should be like this. Fine, but practically this is not possible. My filter response will be like this. Practically it will be tapered. Practically such kind of filter will be possible. We have already seen that thing in our network analysis and synthesis subject. Okay, so if we have oversampling, then we will get some margin in between where we can have this tapered filter response possible. Okay, we can have practical filters possible, implementation of those filters. So you can see here that my filter response could be something like this. Okay, so this taperedness, it has come into the band gap area, and it is not affecting my actual response of the filter. Okay, so that way such kind of your practical filters can be employed to recover our original signal back. So that was all about sampling theorem, the process of sampling, and how do we carry out sampling, the mathematical description of the sampling, and the significance of the sampling. Okay, I hope you have been able to understand that how important sampling is to convert our analog signal into digital signal, because this is the first and the most important step. Fine. So I hope all of you have been able to understand this. So students, after discussing the concept of sampling theorem, now let us move to our next step of elements of PCM system, that is your quantization. Or I told you that the first step for going from analog to digital is sampling, and the second step is the quantization. Let us see to that. So this is our quantization. As I told you in the very beginning, that for representing digital signals, we need discreteness in time as well as discreteness in amplitude. We obtained discreteness in time through sampling. Okay, so when we sample, we have been able to introduce discreteness in time. Now we need to understand what is the meaning of discreteness in amplitude. Okay, though by looking at this PAM signal, we are not able to make out what is the meaning of discreteness in amplitude. Let me explain you. If we have some analog signal, okay, I sampled this analog signal at different instances of time, say time 1, time 2, time 3, and time 4. Okay, so these are my different time instances. I have introduced discreteness in time. But what about the amplitude levels of these samples? The amplitude levels of these samples, there is no discreteness there. This value of this amplitude, it may be anything, say 0.5. The value of this may be 0.1. The value of this may be 0.05. The value of this may be 0.3. Means the amplitude of these samples may assume any value from 0 to infinite. There is a possibility that any value may be assigned or may be present with the amplitude of these sample values. So obviously, if amplitude can assume any value, that means it is continuous in amplitude. But I want discreteness in amplitude. I want finite amplitude levels. For that, we do quantization. Quantization means we will approximate our original signal values to some finite amplitude levels. This is what we are going to do in quantization. We will approximate our original signal values to some amplitude levels. What does it mean? You look carefully at this figure. Here, the blue colored line, this is our original signal. Fine. I have divided the range of the amplitude. The amplitude is varying from say 0 to this level. Okay, so I have divided the entire range of the amplitude into certain finite number of levels. This is say level number 1, okay, level 2, level 3, 4, 5, 6, and 7. So I have divided my amplitude range into 7 levels. Okay, and these levels have been numbered depending on its value at the center of this level. The center of the first level is called 0. The center of the second level is taken 1. The center of third level is 2, then 3, then 4. Okay, then this 5, then 6, and this one is 7. Okay, so now what is happening, or what is the meaning of converting or approximating original signal value to finite level? That means that if the amplitude of my original signal or the voltage value of my original signal lies within this range, any value within this range will be considered a single value, that is the center value. Okay, so for this entire range of this level, I have considered one single value of the amplitude. Fine. Then as my original signal value changes, in the next level, say my original signal values lies in this range. Okay, but I am sampling at this instance. So I am sampling at this instance and the value at that instance of the signal lies in this range, this level range. Okay, in that case, my voltage level will reach in this range, and I will consider the center value of that level equivalent to my finite amplitude level range. Okay, so means these values of my original signal, they are approximated to this finite amplitude level. Then at my next sampling instance, at this point, my signal is present within this level or this amplitude range. Here, for this range, I consider this central value of this range as my amplitude level till the point I remain within this range, or till the time I reach to my next sampling instance. Okay, so during my next sampling instance, say at 6, I'm again in this same range. So that's why I maintain the same level. Now during this sampling instance, that is sampling instance number 8, fine, my signal has reached in this voltage range. So I'll consider this as my finite level. Similarly, this. So what I am doing here, I hope all of you have been able to understand that I am approximating my original signal values to finite amplitude levels. Okay, finite levels. So, and I already told you that this signal range has been divided into 7 or 8 voltage levels. So only those 8 voltage values are possible after quantization. Though in the original signal, there were infinite number of values. Whereas after quantization, means this green colored signal has only 7 or 8 number of values present. So this is how, with the help of quantization, I am able to introduce discreteness in my amplitude domain. And obviously, as I told you during sampling also, that due to sampling, I introduce a deliberate distortion because I have taken finite number of samples in time. Similarly, since I am taking finite number of samples in amplitude also, I am introducing distortion in my original signal. And that distortion due to quantization is called quantization error or quantization noise. Though on one hand side, I tell you that when we convert analog to digital, we are able to control noise. We are able to combat noise. But some distortion has also been introduced because of this conversion of analog signal into digital signal. And that distortion or error or noise in quantization is called as quantization noise. Fine. So obviously we will have to take care of this thing also. During sampling, we will have to take care that we have to consider samples at such rate that my signal is fully recovered without any without any distortion. Okay. Similarly, when I carry out quantization, I will have to ensure that the quantization error or quantization noise should not be sufficiently high that my signal is not represented completely. So I will have to ensure that my signal is faithfully reproduced back or reconstructed after carrying out sampling and quantization when I receive my signal back at the receiver side. Okay. So quantization in itself is a very big topic. If you want to study this topic in detail, then you can refer to sources from internet. Okay. You must have heard of A to D converter. So your A to D converter, whenever we say A to D converter, it is implied that we have sampling involved in that, we have quantization involved in that. So if you study about A to D converter, you will come across sampling, you will come across quantization. Now, as I told you that the biggest advantage that we get when we sample and when we quantize or when we convert our analog signal into digital signal is with respect to noise. The performance of noise is significantly high, or immunity against noise is significantly high in case of digital signal. So how that immunity is boosted or how the effect of noise is significantly reduced in digital signal, that we need to see. See, in this figure, I have shown you first analog signal. In analog signal, you can see that there are infinite values present. It means the infinite number of values are affected by noise. And it is impossible to remove the noise from infinite number of signal values. That's why once noise has entered into analog signal, it is not possible for us to remove noise from that analog signal because we cannot process infinite values. But in case of digital signal, we have finite number of values in time domain as well as in the amplitude domain. Okay, apart from that, we know beforehand that what are those levels. We know this is level number 1, this is level number 3, this is level number 6. Okay. So if noise affects your digital signal, it will be affecting like this. Okay. So as long as the effect of the noise is within this amplitude range or range of the quantization levels, as long as our noise lie in the range of the quantization level, my signal level will not change. Okay, I can say that, okay, this is within the range. So it means this can be removed and I can generate a fresh pulse like this. I can remove this noise and I can generate fresh pulse. So this is how this noise can be easily removed as long as my effect of noise lies within the range of quantization level. Okay, this thing is not possible in case of analog signal. So this is how your quantization process help us in reducing significantly the effect of noise in digital signal. I hope all of you have been able to understand this. Next. So after sampling and quantization, the next is encoding. Okay, so we all know what is the meaning of encoding. So we have done sampling, we have done quantization. Now, once we have done quantization, whatever quantization levels we have taken, we will represent these levels with the help of a binary code. Okay, if there are 8 levels, we can take a 3-digit binary number to represent a level. So we know that if the 3-digit binary number is there, there will be total 8 levels possible. So we can assign a binary code or set of symbols to each discrete level of our quantization level. Okay, this is known as your encoding. Obviously, if we are considering binary code and it is the most widely used one, we represent our sample value with binary code that is in the form of 1 and 0. Okay, so we know that 1 and 0 are represented in the form of pulses like this. Fine. So when we say that 1 is there, pulse is present. When 0 is there, pulse is absent. When 0 is there, pulse is absent. When we say 1 is there, pulse is present, then pulse is present, like this. So in binary code, we will be simply concerned with whether my pulse is present or pulse is absent, because the pulse duration is fixed and the pulse amplitude is fixed. So after quantization, I'll be representing my quantization levels with the help of discrete pulses. Okay, so if we have r number of bits in each sample, okay, then obviously we will have 2 raised to power r number of quantization levels possible. So if we have 8 levels, then each sample will be represented by 3 bits or 3-digit binary code. So this is known as encoding in case of PCM. So this figure is quite informative if you look at carefully here. So this is a black line is our original signal. When we sample, my sample value lies on this uh, signal graph. Okay, when I quantize, it means that signal value is changed to the level that I have fixed. Say this was my original signal value. It has been quantized to a level. This is quantization. Okay, and after quantization, that quantization level is represented with the help of a code. This is code. So this is sampling, this is quantization, and this is coding. So after I have coded, this sample will be transmitted in the form of 3 pulses. During 0, no pulse. During 1, pulse. Then again pulse. So this single sample after quantization will be transmitted with the help of 3 pulses. So this is your encoding. So with this, I have been able to explain the concept of sampling, the concept of quantization, and the concept of encoding. Okay, I hope all of you have understood this thing in a nice way. Next. So this is the complete block diagram of our PCM system. Though like I have explained all the things in detail, so nothing much left to explain now in this block diagram of PCM system. Everything is self-explanatory. I explained you sampler, I explained you quantizer, I explained you encoder, and I told you that my starting point for PCM system is my analog message signal. Now from where this LPF low pass filter has come, if you remember, I told you that in order to sample, I need a band limited signal. Okay, so for band limited signal, I need to pass my message signal through a low pass filter. So this low pass filter will make my signal band limited, and only then I'll be able to carry out sampling. So that's why this low pass filter has been shown here. So this is my PCM transmitter. So this PCM transmitter output given to the channel. Okay, and this is my receiver section. So in the receiver section, as I told you, I'll be having the reverse of transmitter section. I'll be having decoder. I'll be having the reconstruction filter, as I told you in the sampling theorem proof, and this is my destination. So obviously I'll be having one regeneration circuit also. I'll tell you about this in the next slide. Okay. So this is my block diagram of PCM system. Another advantage of PCM system is the use of repeater. Okay, so in case of your digital communication system, we can use repeater. And what is the job of repeater? The job of the repeater is to regenerate the circuit. Okay, in case of your PCM, what happens, we know that the level of the pulses are fixed. Whatever 0 1 1 1 0 we transmit, their level is fixed. And if in between some noise has come here, okay, then what I can do, I can pass it through a clipping circuit. I'll remove that noise and I will generate fresh pulses. Okay, so this way, in case of your digital system, my noise does not accumulate. With the help of your repeater, what repeater does, it reshapes my pulses, it clean up my pulses. So after passing through repeater, my signal becomes fresh. Okay, the noise reached up to that is removed and fresh copy of the signal is transmitted. That is the job of repeater, which we could not use in case of analog communication system, because there once noise entered, it could not be removed. Okay, so that was all about your block diagram of PCM system. We are left with only one small slide next, that will explain the receiver section. Okay, and after that your PCM topic and today's class will be over. Next. So this is the block diagram of PCM decoder. As I told you that in case of PCM decoder, we have three things. One is regeneration circuit, another is decoder, and third one is your reconstruction filter. So in regeneration circuit, what do we have? Once we receive our PCM signal, we have regeneration circuit. So regeneration means three things. We do equalization, we do timing, and we do decision making. I told you that once noise has entered here, let me erase and show you. See, this is what we get at the input of my receiver. Okay, noise is present here. So equalization means I'll be removing this noise. Okay, after passing it through a clipping circuit, I can easily remove this. Means I am cleaning my pulse. This is the meaning of your regeneration, or this is the job of the receiver, to make your pulses fresh or to regenerate those pulses which have been corrupted by noise, provided the noise level remains within the quantization interval. Okay, so this is what happens in equalization. We reshape and we clean up the pulses. Okay, after doing equalization, what is our next step? Our next step is timing. Timing means whatever pulses we have equalized, okay, obviously we need to simply detect whether my pulse is present or my pulse is absent, as I told you. Okay, we have cleaned up the pulses. Okay, so now I need to say one bit is present here, 0 is there, 1 is here, 1 is here. So for this entire duration, I have 1 present. So where should I sample that? Okay, at this instance, I will assume it as 1. So I will consider, or I will detect whether 1 is there or not at that point of time where my SNR is maximum. Okay, so I will sample equalized pulses at those time instances where my SNR is maximum, so that I am able to detect my signal correctly. So after equalization, next is my timing. After I have detected my pulse, then I'll make decision whether the pulse that has been detected is taken as 1 or 0. So for that, I fix a threshold. If my voltage value is more than threshold, I'll take that as 1. If my threshold value is less than threshold, if my voltage value detected is less than threshold, I'll take that as 0. So that is your decision making. So my regeneration involves three things: equalization, timing, and decision making, that helps me in regenerating my transmitted signal back. Okay, so regeneration gives me these things, 0 and 1 continuously. So after I have got those regenerated pulses, then means I am able to generate my code word. So from code word, I have to get back this quantized signal back. Means I need to regroup my code to form a pulse so that my amplitude of that pulse is equivalent to my original signal. Means I have to come back from, see, this is what I want. Say I have detected 011. From 011, I have to come to, say, this particular level, which gives me 3. Okay. Or from 010, I'll have to come to a level that gives me a level 1. Means I'm decoding. So I'm grouping these pulses together to give me a single amplitude value. Okay. That gives me the amplitude of a single pulse. Okay. So I'm going back from coding to quantization. So this is what I'm doing here, that I'm regrouping my pulses, coded pulses, to form a single pulse whose amplitude is equal to the linear sum of all the pulses in that code word. If I do that, I get such kind of signal. Okay, so this is what I get here when I make and connect samples. So after I do that, now you can see that my signal is present as envelope of this quantized signal. So if I pass it through a low pass filter, I'm able to get my analog signal back. So obviously this is not 100% analog signal, but it is approximated version of my original signal, and I'll not be able to notice this discontinuity in my natural receivers. So that's why this signal is nothing but equivalent to the original modulating signal that I transmitted. So this is all about my PCM decoder and all about my PCM system. I hope the concept and the block diagram of PCM system is clear to each and every student. Now the last slide. So the last slide is the merits and demerits of your PCM system. So in case of PCM, my circuit designs are relatively inexpensive. That is one advantage. Another advantage is I told you that noise does not accumulate in case of PCM signal or digital signal, because your digital signals can be regenerated and we can retransmit my error-free signals after my repeater. That is very, very important point as merit of PCM. And because of that, the noise performance of PCM signal is significantly high due to finite number of levels as compared to infinite levels in the analog signal. So though I'm saying that there are so many merits of PCM, it is not free from demerits. In case of PCM signal, PCM signal occupy large spectrum due to the switching of these pulses, but we can control this large spectrum demerit by having higher spectral efficiency through the use of multiple access technique. Okay, so this was a small demerit of the PCM signal. So that's all about concept of pulse code modulation system, PCM encoder, PCM decoder, and the complete block diagram of PCM system. I hope all of you have been able to understand the concept of PCM. Thank you. Thank you very much.